Hi there, I'm Tori Hoehler. I'm from NASA Ames Research Center. My co-presenter is Michael Behrenfeld from Oregon State University. We've been asked to talk today about the biogeochemistry of ocean worlds. And of course, there's really only one ocean world that we're sure has biogeochemistry. We know that's a big footprint here. Biology is a very important part of what goes on in the chemistry of our oceans. We really don't know whether that's the case for other ocean worlds. And if it is, it likely plays a much different role. And that's what we want to focus on today. So there is one ocean world represented in this picture, and that's us. This is Earth as seen from the Saturn system about 1 billion miles away or so. And I'd like to present it in this perspective because I think it reminds us that we're trying to use Earth to help ourselves understand worlds that are very distant and perhaps very different from our own. And therein, I think, lies the challenge in how to do this, right? We need to make the best use that we can of the example that we understand in detail, but to do so being mindful constantly of how different these places might be. And that's the focus that we're going to put in today's talk, to talk about what we understand about biogeochemistry on Earth, and then think about these other worlds from the perspective of how different they are. The same basic principles in play, but perhaps working in a very different way. So the way that we thought we would divide this up is that Mike, who focuses on carbon cycling in Earth's oceans, we'll talk about Earth, and then I'll talk about the rest of the solar system, about which we know quite a bit less, but hopefully enough to prove interesting. And with that, I'll ask Mike to take it away.
Okay, when we think about life on other ocean worlds in our solar system and what we might predict about them based upon our observations on Earth, one of the important factors that we need to think about is the source of energy, or the flux of energy that's available to support life. Within our solar system, we have 7 ocean worlds that we're aware of. They are, of course, Earth, and then 3 around Jupiter, 2 at Saturn, and 1 at Neptune. To get a feeling for the distribution of solar energy and how it differs between these ocean worlds, we can be a bit misled by standard posters such as this one, because they really are not depicting the actual distances between the different planets and the sun. If we were to rescale this according to these distances, the scale would look something like this down at the bottom. So we have the sun over on the left and Earth relatively close to the sun. At Jupiter's orbit, the solar flux is only 4% of that we receive on Earth. Saturn is 1%, and Neptune, which is quite a ways distance, has a solar flux of only about 0.1% of that on Earth. And these differences have major implications for life on different ocean worlds. We are lucky in our fortuitous orbit in that the solar flux is sufficiently large that Earth remains largely ice-free. And one of the important ramifications of that is that solar energy penetrates deeply into the ocean. So the area for light-driven life is large on Earth. Relatively speaking, Earth is also warm and has temperatures that are appropriate for active enzymatic reactions. We have a strong hydrologic cycle driven by the solar flux of energy, and that's important for life because it ensures a vigorous continental weathering and thus replenishment of sequestered nutrients. Another important element in Earth and its support of life is its strong currents and physical mixing. And this is important because it ensures that processes of life and the elements that support it are continuously remixed and do not get progressively separated over time. Life on Earth is, for the most part, solar powered. We have a rich supply of high energy light. And over time, this allowed the invention of a primary production based on an inexhaustible source of electrons, the splitting of water. Photosynthetic life on Earth is driven by wavelengths in the visible part of the spectrum. But even within this part of the spectrum, there is insufficient energy within a given photon to split a water molecule. But what life invented was a means to sequentially absorb 4 photons of energy and then use this combined energy to split 2 molecules of water and produce a single oxygen molecule. So how much energy do we actually receive on Earth, and how well is it used by life? Well, the total solar flux, the top of our atmosphere, is at about 173 petawatts. If we take into account the surface, the fraction of the Earth's surface that is covered by oceans, and we remove the loss of solar energy at the top of the atmosphere due to absorption within the atmosphere and reflection by the atmosphere back into space, and then we take into account the fraction of the total flux that is within the visible band, and finally integrate this over an entire year, we basically receive about 8 times 10 to the 11th terajoules of energy. Converted into perhaps more intuitive terms, that's about 4 times 10 to the 18th moles of quanta. So that's how much light is going to the ocean surface. How much do the phytoplankton get? Well, pigment absorption alone accounts for about 10 to the 17th, 6 times 10 to the 17th moles of quanta. So only about 13% of the available visible energy is absorbed by phytoplankton. Of this absorbed energy, only about 35%, or 2 times 10 to the 17th moles, are used for photosynthetic electron transport, and the rest of it is dissipated largely as heat. Of the photosynthetic electron transport, actually most of it is consumed by the phytoplankton on a time scale shorter than the cell cycle. The net production, which is the amount of energy that's stored as carbon, available for growth or consumption by predators, when integrated over the annual cycle for the entire photic layer of the global oceans, is only about 10 to the 16th moles of quanta. In other words, the net efficiency of photosynthesis in the ocean, converting available visible wavelengths into stored carbon, is only on the order of about 1 or 1.4%. Nevertheless, this is a pretty significant flux of organic matter, equivalent to about 50 petagrams of carbon per year. What's particularly amazing about ocean ecosystems is that primary production of 50 petagrams is accomplished with a standing stock of phytoplankton on the order of only about 0.5 petagrams, or about 10% of annual NPP. What this means, of course, is that the turnover rate of phytoplankton is very high, on the order of a day to a week, and recycling of nutrients is very fast. This rapid tempo of life in the plankton is possible, in part because of the waste product of photosynthesis, oxygen. There's a tight coupling between predators and prey in the ocean, and this causes standing stocks of life in the ocean to respond rapidly to changes in environmental conditions. And we see this beautifully in the satellite record shown on the left of surface chlorophyll concentration. As the environment changes with the season, on land as well, life on Earth responds to that. And this responsivity of the biosphere is a clear signature of life on Earth. And it only exists here because Earth is a high energy planet. Ecosystem processes also cause the distribution of life to deviate from that of the solar energy flux. And instead of just mirroring the energy flux, it carries additional signatures of growth limiting resources and physical transport systems. If we look at the variability of biomass in the ocean, concentrations of phytoplankton span 3 orders of magnitude in concentration. If we were then to look at this instead as the biomass per unit of area of ocean surface, the variability is actually quite a bit smaller, a bit over 1 order of magnitude. One of the things I always like commenting on is that this variability in biomass per unit surface area would actually be a lot smaller if not for the fact that water itself is very efficient at absorbing light. So I like to think of phytoplankton actually compete with ocean water for the energy available for light. A competition that's nowhere near as strong in terrestrial systems. We see that many of the signatures of life on Earth exhibit similar distributions, and they reflect the extant resource supply. But this is not always the case. Some signatures of life on Earth can be found nearly everywhere in the ocean, and their distributions are largely independent of their source. I mentioned that ocean phytoplankton fix about 50 petagrams of carbon annually, but only about 6 petagrams of this, or 12%, is actually exported out of the photic layer and is available for sequestration. And of this, a large part is actually degraded and respired in relatively short order. However, there are some biomolecules that are highly resistant to degradation. They can persist for hundreds or even millions of years. And these refractory compounds of life are far more dilute than plankton biomass, but their persistence means that they will be widely distributed and more uniform across ocean basins. In some cases, like I mentioned, bearing little resemblance to the distribution of their living sources. Thus, if we take Earth as an example, finding evidence of life on another world does not necessarily require knowledge of where that life is. Only a robust chemical trademark of life, and quite likely high precision measurements. The proximity of Earth to the sun supercharges life's engines, supporting an astronomical number of individuals. And this huge number of individuals means that there is a rapid pace of evolution on Earth. Within only about 1.5 billion years after life first emerged here, cells were already using solar energy to extract electrons from water and creating an oxygenated world with massive ecosystems. Biology of this high energy Earth, which has been going on for a long time, is a dominant force in its biogeochemical cycles. And we make observations across nearly all spatial and temporal scales, from molecules to space, that allow us to mechanistically estimate fluxes of biogeochemistry on Earth. While the high energy ecosystems dominate Earth's biogeochemical cycles with a capital Bio, life here most likely emerged in and can still be found in low energy environments where enzymatic rates and sources of energy are barely sufficient for cellular maintenance, much less rapid growth. So the question I'm thinking is, if we were to remove all signatures of Earth's high energy ecosystems that I've been talking about here, would there still be a biosignal in elemental cycles? If so, what would it look like? And how would we find it?
I want to pick up on a few of the threads that Mike has established. And I thought I would start here with what I think is a really cool animation that Mike showed in his talk as well. What we see here is the Earth working as a system of coupled processes. And you see biology and the changes in biology represented as, I think, an interplay of resource availability, environmental and ecological stresses, and physical transport. And I think that we can expect those same factors to be in play in the geochemistry or the biogeochemistry, if it exists, on other ocean worlds, but maybe playing out in a very different way. And that's the way that I want to approach this part of the talk. So with that, I want to talk about the maybe biogeochemistry with a little b of ocean worlds beyond Earth. And as Mike has indicated, we know of several now. So you see 6 of them represented here. Our own Earth, of course, and several other ocean worlds. And if you can read the fine print, you'll see that they vary in the way they're described. Some are described as active, some are described as locked. This largely refers to where we believe the oceans are, whether they're in contact with a silicate seafloor or locked between thick layers of ice. And as diverse as they are, and as interesting as they all are, I want to talk through them in sort of a comprehensive way. So I want to talk about them as a general set. And let me start here with a little bit of perspective about Earth. So we, of course, think of Earth as an ocean world, and it is, but comparatively speaking, Earth is quite a dry world. So if you were to scoop up all the water from Earth's surface and represent it in a sphere, this is what it would look like. And relative to the ocean worlds of the outer solar system, water is quite sparse here. And Mike mentioned earlier on that Earth has fortuitous attributes in several ways. This is one that we might add to the list because the relative scarcity of water here might be seen in a just right kind of light. It allows us emergent continents, and that in and of itself creates all kinds of important aspects of our biogeochemical cycling. So there's an estimate of water content by percent volume that my colleague Steve Vance has made. By that metric, Earth has about 0.1% water, and each of the sort of ocean worlds that we consider in the outer solar system are greater than 10% by volume water. We're talking about very deep oceans, very significant amounts of water. And that's important because on Earth, you can think of the rocks as really holding sway over the chemistry of the oceans. The relative abundance of water to rock is very small, and the rock here is constantly replenished by tectonism. On the ocean worlds, that actually might be reversed. So when you start out with such a large quantity of water relative to rocks, it may be that the chemistry of the water, the initial chemistry of the water, has a great deal to do with the evolving chemistry of the oceans there, and that geophysical, geochemical change, and even biological change have to work much harder to introduce any significant change in the chemistry of such a large body of water. So the way that I thought I would do this, rather than try to give you an overview of all of the different ocean worlds and their diversity, to go broadly but shallow, I thought I would try to do a case study. And for this, I want to use the small moon of Saturn called Enceladus, pictured here. So there are a couple of places we can start with Enceladus. The first is that Enceladus is small. You see it represented here relative to the United Kingdom and the continent of Europe, and it fits quite handily in the North Sea. So to give you a sense of how small it is, a convenient number to put in your head is that the gravity at the surface of Enceladus is about 1% the gravity of the surface of the Earth. And what that means is when Enceladus formed, there really wasn't a whole lot of energy involved in putting that moon together, right, in the process of accreting that moon. So not a lot of internal heat to begin with. And the surface area to volume ratio of Enceladus is very large in comparison to Earth. And this means it has the potential to cool off quickly and that it doesn't retain very much heat. So relative to our own planet, which has robust radiogenic heating, Enceladus is expected to really not retain very much heat at all. Enceladus is also far away, so it's about 1 billion miles away in the orbit of Saturn. That gives it a surface irradiance of about 1% relative to Earth. And this has led to the expectation, or previously led to the expectation, that there should be an uninteresting ball of deep frozen ice. So enter the Cassini spacecraft, which spent 13 years in the Saturn system. And early in the going of that grand tour of the Saturn system, an interesting discovery was made about Enceladus, and that is, as you see depicted here, that there are plumes of ice and gas emerging from the South Pole region, collectively amounting to about 200 kilograms per second, which suggests that this supposedly dead world is in fact quite active. And as a colleague of mine likes to say, Enceladus is far more interesting than it has any right to be. I think this is actually kind of characteristic of the ocean worlds of the outer solar system in general. Going into the exploration of those worlds, we've often thought that, you know, they may just be frozen, dead, uninteresting places. And in fact, the more we explore, the more active worlds, the more interesting ocean worlds we find. So this is the current picture of Enceladus after many, many flybys of the Cassini orbiter. We now believe that Enceladus has a global ocean that's beneath tens of kilometers of ice. It's actually a salty ocean, so the instruments on board Cassini, although never designed to examine ocean chemistry because we simply didn't expect an ocean world to be there, the Cassini team has done a remarkable job in investigating the chemistry as represented in these plumes of emerging ice and gas. And so we know that it's actually a salty ocean, perhaps 10 to 40% of Earth's ocean salinity. That's significant because it implies there's been a lot of reaction of water with rocks, just as on Earth. The salinity in the ocean comes from ultimately from the reaction of water with rocks, and pretty extensively so. So you need to react at least about 10% the mass of rock as mass of water to get up into this salinity range, if not higher. There's at least a little evidence of hydrothermalism. So the way that people often imagine these worlds to work is that internal heating comes not primarily from radioactive decay as it does here, but from dynamical forces, tidal heating, for example, and that some of that might be expressed in the form of circulation of water at high temperature, as in our hydrothermal vents here on Earth. And remarkably, I think there are some observational constraints on the pH of the ocean. It's mildly to perhaps somewhat alkaline, pH of maybe 9 to 11. We have constraints on the abundance of dissolved carbon, nitrogen, and sulfur as elemental requirements of life, and even on the availability of chemical energy in the redox couple of hydrogen plus CO2, which could fuel, for example, methanogenesis. And so this has gotten people very excited about the possibility that Enceladus could host life, and has raised the interest in exploring this world a little further. What I want to say is, even though the focus here is on this one specific world, Enceladus, a lot of what I'm describing characterizes our experience with ocean worlds more broadly. We've come to see them as interesting places and potential abodes of life, and all of them have become interesting potential destinations for further exploration. Nevertheless, interesting or not, Enceladus is still small and it's still far away, and that carries important implications for physical, chemical, and maybe biological processes. And that's what I want to talk about here. How does being small and far away impact the way that biogeochemistry might play out on this world relative to the way we experience it here on Earth? And so the first and most obvious thing is that the irradiance of the liquid water environment is much different. So on the left, we have a photo that you could take across much of the surface area of Earth. And we see several things represented in that process or in this photo. We see dynamical movement in the ocean water. So we see waves, for example, that are ultimately wind-driven, and that's ultimately a product of the input of solar energy. We see clouds represented on the mountaintop that are evidence of a hydrologic cycle that in this case will weather that island and deliver some of its material to the ocean. So a robust weathering flux of material. And if you could see closely enough, you'd see reefs represented in the foreground of the picture, and there's a direct interaction there of life with sunlight energy. So on the right, I've taxed the limits of my artistic ability to give you an artist's conception of what the ocean interior of Enceladus would look like. And of course, there's no light there. And there are important implications for both biology and for physical and chemical processes. I want to spend most of the time on the former, thinking through the implications for biology, and a little bit of time at the end on the latter. So let me pick up a thread that Mike discussed in his part of the talk. And that is to think about how the energy that's available in sunlight fuels our biosphere and what that implies for the cycling of the elements. And I want to think this through in quantitative terms. So just to review a few of the numbers that Mike expressed, I'm going to put them in subtly different units here. But our planet overall receives a top of the atmosphere irradiance of about 173,000 terawatts. And if you scale that just to the portion of the Earth's surface that's covered by the oceans, that's about 121,000 terawatts if all wavelengths are considered. Biology absorbs about 2,200 terawatts of that in the oceans. And as Mike described, a lot of that is rejected to heat, maybe a third or so is actually used to fix carbon. And when that carbon turns into net primary productivity, if you think of that as becoming available to aerobic respiration, that pumps about 70 terawatts of energy into the biosphere that comprises us, right? The consumers of that net primary productivity. And this is the context that we have when we think about how life impacts a world, this massive flow of energy through our biosphere. When we think about these ocean worlds, of course, that flux isn't there. And instead, a lot of people believe that any biosphere in these places would rely on something like our hydrothermalism. So in our case, this is a flux of reductant that's sourced in our crustal material into an oxygenated ocean. Some of these ocean worlds beyond Earth may have oxygen in their oceans, some not. But at any rate, people envision this as the principal mode of supplying energy to life in those oceans. And actually, on an aerial basis, the heat flux in some of those ocean worlds is not so very different from the aerial heat flux that we experience here on Earth. And if that's turned into reductant in about the same efficiency, you might look at Earth's hydrothermalism as a stand-in for the delivery of energy on these ocean worlds. And so I've tried to do a little bit of a back of the envelope version of how much energy is delivered if you add up all of the reductants, so all of the hydrogen and the hydrogen sulfide and the methane that comes out of hydrothermal vents across Earth's ocean, and allow that to be available for aerobic metabolism. And the number that you get is about 0.006 terawatts, so about 4 orders of magnitude less energy than flows from net primary productivity into our consumer biosphere, and about 5 to 6 orders of magnitude less energy than is flowing through our photosynthetic biosphere. And that has to have consequences for life, right? The way that we think about life on Earth, the way that we're surrounded by a robust biosphere that is fueled by this huge influx of energy, has to play out differently in an ocean world where the energy flux is 5 or 6 orders of magnitude lower. So let's try to talk about that in terms of elemental cycling. And I want to come back to this image that I showed earlier from a slightly different perspective. And this is a point that Mike made in his talk. I think it's an important point to make again. What you see here is a change in Earth's biosphere that is observable from space and occurs on a months-long time scale or shorter. We're almost literally watching the Earth breathe in this animation. And I think that's remarkable, and it is only possible because of exactly the magnitude of resource flux that is available to drive this level of change in the biosphere. This is the intuition that we have about how an inhabited world works. And in terms of carbon cycling, so just to get back to some numbers that Mike mentioned, the global photosynthetic biomass as represented in the oceans turns over on a time scale of days, right? The entire biomass is turning over on a time scale of days. And that's because there is so much resource flux flowing through that biosphere that enables that high level of biosynthesis. I thought it was also interesting to think about that rate of primary productivity in reference to the organic carbon in the ocean and the inorganic carbon in the ocean. And so if we think about all of the dissolved organic carbon represented in the ocean, that equivalent amount of carbon could be cycled through net primary productivity in slightly more than a decade. And all of the dissolved inorganic carbon in the ocean could be cycled through primary productivity in about 700 years, less than the turnover time, the physical turnover time of the ocean. What about a world like Enceladus, where there actually have been some estimates made of how energy flux on this world could support biosynthesis? And if you take those estimated rates of biosynthesis, and I'll say they're very poorly constrained, the rates that are represented in the literature span about 5 orders of magnitude overall to 6 orders of magnitude. Taking the most optimistic of those rates, which are something like taking most of the silicate mass of Enceladus, allowing it to react with water and delivering that associated hydrogen as energy to the biosphere, suggests that in order to turn over the bulk ocean dissolved inorganic carbon on Enceladus, and there actually are estimates of the DIC concentration there, would require something like 100 million to 10 billion years. Remarkable long rates in comparison to the Earth. And to turn over ocean organic carbon, so we don't have very good numbers to constrain organic carbon concentrations, but realize if we have this much water delivered, perhaps from comets, which are very organic rich, there's the potential to have a very large stock of organic carbon there. And I just have reference numbers here to a 1% value for carbon in the ocean. And to turn that over through the biosynthesis that might be possible on Enceladus would take more than 1 billion years. So perhaps as long as the age of the solar system. So the impact that biology can have on the cycling of elements in our system and in the ocean worlds of the outer solar system is dramatically and orders of magnitude different. Let me come back now to the impact that the size and the distance, the distance away from the sun that Enceladus has on physical and chemical processes. So what you see here represented is a satellite image of the Ganges watershed. And so at the top of the picture, you see the Himalayas, you see the Ganges Delta, and what you're seeing represents several important things about the way that our biogeochemistry works. So we have a planet that is capable, that has enough mass and a low enough surface area to volume ratio that we can melt silicates within the interior. That means that we can differentiate the material from which our planet is made into continents and ocean crust. It gives us chemically different reservoirs, and it gives us emergent continents. The robust hydrological cycle that is possible here because of the input of solar energy and because of the emergent continents weathers that material and delivers a flux of resources to the ocean. And that riverine flux is a significant term in our biogeochemistry that cannot exist on these other ocean worlds. And so we need to think very differently about the way that factors might play out. And so I think this is ground that Wanying and Jeff will cover much more thoroughly in their talks. And so I just wanted to kind of introduce a few considerations maybe for discussion in the breakout session. So certainly we have to think about the formation of these worlds and the crustal composition as playing out very, very differently because of the large difference in mass between the two of them. As I mentioned, the fact that we can have continents here and weathering of those continents sets up resource fluxes that will be dramatically different here versus elsewhere. And of course, our ocean circulation is driven in many ways by the input of solar energy, so creating wind-driven circulation, and thermohaline circulation that depends not only on the formation of density gradients, but also on buoyancy. And that buoyancy, of course, depends very much on gravity, which is, as I said, about 100 times greater here than it is on Enceladus. And so although we think of processes, the basic processes that interplay in biogeochemistry here and possible biogeochemistry elsewhere as having the same knobs to turn, the way in which those knobs are turned, the magnitude with which those processes interact may be very different. And so to close, I want to come back to this image one more time, and I promise this is the last time. Here I see it from a slightly different perspective. So what you're looking at here represents an amazing capability to observe the way that elemental cycling plays out on this world. And the numbers that you heard Mike express in his talk for net primary productivity, for example, represent not only terabytes or petabytes of data that are collected at this level of observation, but also thousands of individual measurements that allow us to relate these satellite observations to the way that things play out in the oceans. And so when we think of models here, we think of something that allows us to test the understanding that we've built through extensive observation and perhaps extend that understanding modestly in a testable way to places that we've yet to observe. The situation is very different when we talk about the ocean worlds beyond Earth. As I mentioned, everything that we know about the chemistry of Enceladus is really fortuitous and the result of a remarkable ability of the Cassini team to make something out of instruments that were never intended to do ocean world observation in the outer solar system. And there, then the capability to model becomes much more important. It's the primary thing that we can do as informed by relatively limited and relatively large scale observations. And so I think to end, maybe I'll try to articulate a question that Mike also articulated, and this is something I think that we can carry into the breakout session. Do we understand, for example, earthly biogeochemistry in sufficiently mechanistic terms to allow us to predict what an uninhabited Earth would look like, or what a non-photosynthetic version of Earth would look like? Are we that confident in our models? Do we understand the interplay of these processes of resource availability and transport and stressors well enough that we're able to confidently extrapolate to different ocean worlds? And I think that really is the key for gatherings like this, where we're bringing together Earth scientists and planetary scientists, is to leverage the great knowledge that we've developed about how our system works, take stock of the fact that these other worlds are very, very different, and nevertheless do our best to put those two things together to build our understanding. Thank you.